Hey guys, you know, I think I've said this many times already, but it's been a while. What I have here is quite an interesting mechanism, and I like to call it the matter because it's mad, or no, it's mystery adder. But what the mystery adder does is it does instant addition. So what that means is if I put an input on this side, it instantly comes out the other. Unfortunately, I had to put a comparator here because for some reason, even though the redstone's not flashing, a repeater can still power. So this blocks those bad signals and only gets the proper signal. So the pulse comes out as 1.5, but even so, the adder does have a small reset time, and I'm going to show you how negligible it is. This is it, by the way. It's so simple. I'll actually go through what each component does. So first, the input. And this input is just a pulse regulator. It gets it to 1.5, and then it's an instant 1.5, so it helps this go up and down. As this goes up, it makes this XOR gated main. This is a retracting XOR gate, so if you retract, it gives you instant output and works really well. And it just feeds into this column right here, and then this is our carry-in. I haven't put it in yet, but that's the carry-in. So each of these bits or XOR gates have a generate signal that goes into them, and yeah, it just feeds into here. Because for a full adder to work, you need 2 XOR gates, 2 AND gates. The 2 AND gates are for the generates for each XOR gate, and the 2 XOR gate determine the A and B inputs. So if you had like 1B here, 1A here, it makes a 0 and carries it to the next bit. Yeah, so this is an instant adder. And and right here, this is just a register to capture 3 calculations. As you're going to see, I'm going to show you how fast 3 calculations for these individual numbers are. This is a 16-bit adder. So, I mean, the width of the adder is 4, so it's basically like the classic adder, although it's faster, very fast. The carry is instant, by the way. Oop. Yeah, instant carry as well, because I'm using retraction logic. That resets fast. Okay, so without further ado, I'd say we put in some fun numbers to play with, and this is our input panel. This is just for testing purposes. If I was just to do normal data, I would just have synchronized inputs. It would just go in, pop out, and get your data instantly. So, right, so A and B, this represents the individual bits. So this is 1, 2, 4, 8, 16, so on. So I'm going to do the classic problem for the first one. So we're going to go ahead and do 5 plus 3. So we need 1A and 4A. And then we're going to need 1B and 2B. So that'll be our first calculation. So keep this in mind. It's going to be 3 plus 5 equals 8. We'll find that out later. For the second input, I would like to do a whole carry. So we're going to go ahead and add 1 to the A, 1 to the B, and then for the rest of them, we're just going to do A. And what this is going to do is it's going to create a 0 here, and then it's going to carry the number all the way to the end so we can see how fast the carry is. So we put 1 here, 1 there. Yeah, so this is Slimestone at its finest. Not as well. It's pretty neat. I'm glad that I made it. So let's go ahead and put this here. These inputs. Not the best redstone in the world. It takes a while to reset the actual input because I just whipped it up to showcase it. So here's what's going to happen. This needs to be a 0. It's going to carry the bit all the way over here to here, and it'll just become the 16th bit. And maybe for fun, we'll do what number should I do? Like 20 or something? All right, we'll get 4. and 16. So 20 plus, let's do 20 plus 15 to get 35. So 1, oh, B. Yeah, that's right. And that. So I'm going to put a sign down so we know what's up. So it should be 20 plus 15. And then this is just to check the carry speed, which is less than a tick. So you won't notice anything in the carry. And then 5 plus 3. So yeah. Alright, let's go ahead and just flip the switch and see how fast we can get to the other side. And it's done. Nope, that's it. 3 calculations that quick. Alright, so as you said, 5, or what did I say? 5 plus 3 equals 8. So we read 1 plus 2 is 3. Plus 4 is 7. No, I'm not reading that properly. So 1, 2, 4, 8. I'm sorry, I'm just being, I'm weird. I'm out of it. So yeah, 1, 2, 4. This is the 8th bit. And then as you saw, we got our extreme carry, just got bam, just whipped right over there really fast. And I'll do this again just so you could see it. And the last number should have been 35 if I put it in properly. So let's see. We got 2. And then let's see, this is 16, 32 right here. 34 and 35. So yeah, we got all 3 of the answers correct. And yeah. This thing's mad. I love it. Maybe we'll do another run. Oh yeah. On the falling edge, it does another calculation right here. Yep, that's 3 calculations. It just goes boop, boop, boop. There's no lag. So this thing's very efficient on bad computers because I use slime blocks. Yes. So let's just do this one more time, and then maybe we'll do another input. There you go. Yeah, I just wanted to see that. Alright, so there we go. Yeah, so I got nearly the best of both worlds, except there's still one thing I would like to make with this design and a change. For one, I plan to remove this comparator sometime. And that way I could chain a bunch of these instant adders to make instant multipliers and instant dividers and all that. Because you can do that. Yeah, so what these observer blocks here do is actually reset it just resets the pistons fast, essentially. Now, I had to change the pulse here to make this carry logic fast. So what happens is when the XOR gate gets 2 on datas, then it ANDs the input through one of these 2 pistons. And if the piston retracts, then the redstone dust goes up into the next thing. And then when this pushes up, it instantly retracts and so on. It's basically an update chain. If you practice a lot of logic with pistons and zero ticks, you would understand how the update chaining works. Okay, you know what? We wanted to put something different, didn't we? So okay, maybe we'll put a different number in there for the first one, perhaps, and then we'll call it good. Okay, should I do? Man, I don't know what I could do. Let's do. I don't know, an 8, well, I gotta do some number. I'm trying to think of a good one. What if I do something that would cause bits to shift over? That might be a good one. We can do like 15. We can do 15 plus 15 here. And basically, you actually could treat these individual sections as individual adder bits if you cut the carry signals off in between each of these. So this adder could become a quad-core machine if desired for 4-bit stuff, but I'm not interested in that. So let's just go ahead and get those. So that's the 1, 2. So that's 15 plus 15, and then we'll do like, we'll do something over here where we require a long carry, just for the heck of it. You know, it's just for fun, really. That's what this machine's about. And then we'll just do something to get the bit off the screen. Alright, and I gotta erase this thing because it's fast. And it's done. Okay. And yes, so there you go, 15 shifted over because 15 plus 15 is 30. There's 30. And then we did that thing where we carried the point to here, and then the 1 plus 1 is off, so it carried out. And there you have it. So, I hope you enjoyed the Matter. And if you want to see a smaller version of the Matter, just comment me, hey, I want a smaller version of the Matter, and then I'll make a tutorial on this, on that finalized Matter. Because I want the Matter to use the new honey blocks. Well, I could use the new honey blocks instead of slime, but the thing is, honey blocks can now slip past slime. That might make it smaller, so we'll see. I don't know what I can improve with the Matter, but I'll do stuff with it. Mainly I developed the Matter because I need it for one of my computer projects that I've been working on. Alright, you all have a good one. See you later.